Hey everybody, I think we're live here. Good to see you all again. We got Aaron and Steven like usual, but we also got two additional guests here. Michael, who is the lead of the what we call the interoperability team here at Avalabs, and then Matthew, who's also on that team. Both of them are working on Teleporter. So one of the things we're going to talk about after the latest AvalancheGo release is the latest and greatest with Teleporter. A lot of people have been asking questions about that, and who better to talk about it than the people building it? Yeah, we'll go right into Cortina, and then from there we'll get into that. So let me share my screen here. All right, Steven, you know the drill.
All right. We added some pull gossip. So in the latest release, Cortina 17, we had really been pushing off this optimization for quite a while, for really no good reason. I think that we just didn't think it was probably going to be as sick as it was. And then when we started actually getting around to it, it was a pretty solid improvement. So we historically, the way that kind of the block gossip works in the Avalanche network is the block producer will create the block, and then it'll immediately start the querying process, which, if you're familiar with snow consensus, essentially that works by sampling some small constant number of nodes, and that actually notifies those nodes, oh hey, here is a block that exists. They will then start the querying process and query random nodes and ask them their preference. So this works as a push-pull kind of mechanism. So we are pushing new information to you. And then also, if you happen to query someone with something that you've never heard of, you will pull that information. So for the validator set, we've always had this kind of push-pull gossip mechanism that really efficiently distributes blocks throughout the network. However, for non-validators, non-validators are never queried. So they never kind of participate in this push-pull mechanism. In order to get around that and notify non-validators of blocks, what we would do is periodically gossip whatever our latest accepted block was on the network. So every node would periodically gossip their latest accepted block. And that was just kind of uniformly to the network, to the P2P network. And so non-validators would kind of like eventually hear about that and then start the querying process and learn about the blocks. That's essentially a push-only mechanism. So essentially a non-validator has to wait until they hear about some new block that gets pushed to them in order to then kind of catch up and synchronize. And so rather than doing a push-based mechanism, this switches it to a pull-based mechanism on the validator set. So what that ends up meaning is the non-validators will kind of periodically say like, hey, is there anything new on the network? And that ends up significantly reducing kind of the tail, like say P90% of like how long it takes for non-validators to learn about a block. And so on average, we see that this reduces the kind of observed time to finality for non-validators on blocks by around, I think we saw like 20 to 30% or so. And because most nodes that are used by wallets are actually non-validators, this very tangibly increases the speed and like UX feel of wallets being used on the Avalanche network. So this was a really kind of long-standing like to-do that we hadn't really gotten around to. And then when we finally started seeing the numbers out of it, we really kind of highly prioritized getting that out as soon as we could.
The joke I always tell when Steven introduces a change like this is how many other like little optimizations are you hiding around the code base? So when we say make it faster, you can just pull them out. So this is an example of one of those things. I think the term we used when we were looking at it was a win-win. Like there was no trade-off. It was simply just better than what was done previously.
Yeah. So I focused a lot on kind of the latency here, but this also reduces the bandwidth usage on nodes because it doesn't actually in this PR reduce the bandwidth usage, but in the after the next upgrade, we will fully remove the validator put gossip that we are still sending to basically support non-validators that are running older versions than this. And once we do that, we should see a noticeable decrease in bandwidth of put messages as well. Because previously we were just kind of like sending blocks out into the void. Maybe this person has already heard of this block, who knows? Whereas now we're only going to be sending block bytes if that person explicitly asks for them because they don't have it. So this is, while in this PR it is not explicitly a bandwidth saving change, it unlocks in after 111 activates, it unlocks another bandwidth saving change. So it is definitely a kind of a win-win, and we're definitely really happy to have gotten this in before Durango. I think that's all I really wanted to talk about with the pull gossip stuff. I think another thing to shout out in this release is some people are running into issues state syncing the C chain. So that included a fix in the state sync client. There was a regression on how we were handling the bonus blocks from the February 2021 incident. I think it was 21. So that was a throwback to dig back into that chunk of the code, but that this also include that regression fix.
Yeah, there's
and
also
then-
one more fix in the queue for a different issue that someone pointed out with state sync that's also coming in the next release, which should be the next few days, hopefully.
Yeah, currently some people are seeing some unexpected warn logs due to message size constraints. So if some big blocks get passed through, then it doesn't serialize them correctly. So that should be patched in the next release as well. I think aside from that, those are kind of the major two things that I wanted to talk about here.
One of the other big ones to call attention to, just from people playing around locally with subnets, is this change that Felipe got in around adding the BLS info to the Genesis file. So in many cases, if people will run CI where it involves like spinning up some sort of subnet and doing stuff with it, ourself included. And right now, the local Genesis, or previously the local Genesis, didn't actually include any ability to provide a BLS key, or maybe it just didn't. Maybe there was an option earlier on, but we changed some stuff. And so what ended up happening was, like, if you look at the HyperSDK CI, we create a local network, add a subnet, and then we need to add a bunch of new validators that have BLS keys registered that then can participate, because we test some of the messaging between subnets. With this change, we don't need to do that. So it cuts the CI time by like a few minutes usually, which is huge for just faster testing.
One quick clarification: we still haven't actually added the BLS keys to the local network yet. So this added support to provide them for custom networks. We will probably be changing the default local network to include BLS keys very shortly. So yeah.
Good. Yeah. I'm trying to think, is there anything else on this one? Oh, the other quick one to call out as well is probably that we can move right into the teleporter stuff, was this extra documentation that Steven added around storage growth over time. So over the last few weeks, people have seen a clear increase in transactions on the network. There were two features added to help with, well, one feature added to help with this, which is now you can optionally index transactions. So if you are a validator, for example, and you'd never like use the API on your validator to like query transaction history, you don't need to actually index it. And this can take some extra load off your database. So that's a new flag you can now use. But it reminded us as we were working on this that our README was not as clear as it could be around like storage usage and storage usage growth over time. So this is something we're working on with like MerkleDB and Firewood to reduce the overhead of managing the active state. But nonetheless, as more blocks are produced, more transactions are produced, whatever, the disk usage of AvalancheGo will grow over time. And so if you start off somewhere and then you start adding more transaction activity to it, particularly like more state checkpoints, you're going to see your disk size increase over time, typically the longer that you're running the node. Again, like we said, we hope to improve that shortly with some changes to the database layer, but still you will see storage usage increase. So if you, for example, provision a validator and then never check its storage again, eventually it could run out of space and your validator will shut down. So it's something just to keep an eye on over time, and something like we're very sensitive to it. Also know that people obviously don't want to pay as little as possible to run a validator, and that also the cheaper validators ought to run, the more decentralized the network can be. So it's something that's very important to us as we like work on different development here, but something in the meantime just to call out.
Yeah, so this is different than like the actual like required state size increasing on the chain as well. This is more commenting on the fact that the way that the C chain manages state currently, even with pruning enabled, it will not do a perfect job of removing unused state. So this is why some people have gone the route of either using the offline pruning flag periodically or periodically resyncing their node to just get what the current state requirement is.
The HyperSDK experiments have certainly pushed our thinking on this one, because you can exhaust a 1 terabyte disk in like a day. So you got to be more careful about how you manage that on disk information. But as we've mentioned before, like some of the learnings from the HyperSDK have continued to trickle down into AvalancheGo with different performance related improvements there that just make sense, which we may not have known were like as much of a bottleneck as they were. Cool. All right. So Teleporter. Oh, actually, before we do that, Aaron, is there anything you wanted to note on the C chain with the latest release? I know that there was a big merge that you had as well.
Yeah, the other big thing, which I guess, I don't know if it's actually included in the release notes, but we've also included Warp on Core ETH as well. So this is planned to activate in the D upgrade on the C chain. And actually for the local network, Warp is already activated by default, since on the C chain, we activate the D upgrade from the Genesis. So if you want to play around with it, you can start it on the C chain now, on a local network, to reemphasize.
And that's a great segue. All right, Michael, I will turn it over to you now on what you want me to point to. But for people that aren't aware, Teleporter is at this link, and I'm going to share it in the chat so you guys can check it out. Also going to share the demo built by Warp. And so we had hoped to talk a bit about like the upgrade strategy with Teleporter, but I think, Michael, it may make sense to go into a bit more background on reminding people what Teleporter is, what Warp is, and how this all fits together.
Yeah, absolutely. So just as context to get to the Teleporter upgrade strategy, Teleporter, which I think we've talked about on previous calls, is the EVM cross-chain messaging protocol built on top of Warp messaging. So the super shortened version is that it allows you to call smart contracts on other EVM subnets within Avalanche. And it does so by interacting with the Warp precompile and delivering a message to the destination that has a BLS signature, validating that the subnet the message was sent from has a certain percentage of stake that's willing to attest to the fact that that message was sent. Teleporter is built as a smart contract within the EVM that's going to be deployed to the same address on every chain, such that you know the same bytecode is at that address. We're deploying it, or planning on deploying it, using Nix method, which, if you're not familiar with, is a really interesting technique for getting a contract deployed on every chain at the same address. I think we can link some documentation to it within the repo. But that's a pivotal point of the Teleporter design, is that it only sends messages and receives those messages at the same contract address on the multiple chains. I won't go into the various other features of Teleporter. I think we've covered those in the past and they're documented. What we really wanted to touch upon is the Teleporter upgrade strategy. And so to kind of set the table for that, the contracts, like I mentioned, are deployed at the same address on every chain. Applications wanting to use Teleporter really just need to call the send cross-chain message function at that contract address. We have some examples of how to do so within this repo. We have an example, ERC20 bridge, for instance, that's built on top of Teleporter. I'm actually pretty proud of how easy it is to write applications on top of Teleporter, and I'm super excited to see what people build. On the receiving side, then your contract just needs to implement a receive Teleporter message interface and only allow the Teleporter contract address, which again is the same address across all chains, to be the only address to call it. And that's great until we would need to change that Teleporter contract address. And why would we need to change it? Well, if we want to have Teleporter v2, if there's any bug that we need to fix, if there's a new feature we want to add, et cetera, et cetera. There's any number of reasons why we might want a new version of the Teleporter contract. But if applications are pointing just to the old Teleporter contract address, that would basically lock them in to only ever being able to use that single Teleporter version. So we wanted to provide a route for applications to be able to easily switch to use later versions of Teleporter, which would be easy to implement at the application level just by providing some admin the ability to update the Teleporter contract address. So, your contract's currently calling send cross-chain message on 0xABC. Now it's going to go 0xDEF, what have you. But that obviously provides or is dependent upon there being some admin with the ability to change the address. And the ability to change the address that is sending and delivering messages is the ability to deliver arbitrary messages, because you could point your application at a contract that delivers fake messages. And we did not want it to be the case that applications built on top of Teleporter to have an upgrade path needed some extra authentication mechanism, needed some admin or some multi-sig. We thought that really reduced the novelty and the ability to create truly decentralized cross-chain applications. And that was the problem that we kind of set out to solve here. And I'm very excited with what we came up with. I think it was maybe Patrick's suggestion originally was what we now call off-chain warp messages, which is a warp message sent by a subnet that's not actually originating from an on-chain transaction. So typically, validators of a subnet are willing to sign any messages for the subnet EVM specifically, any messages submitted to the precompile in an accepted block. So you need to send a transaction on-chain that calls the warp precompile to send a message. Once the validators accept that block, they'll be then willing to sign that message. But off-chain warp messages are messages that validators are willing to sign that don't originate in a transaction on-chain, and they can be used as a form of really off-chain governance. And we want to leverage that to then provide this upgrade strategy. It can really be leveraged for many further use cases down the line, and I think that's what's the exciting part of this design. But we'll turn it over to Matt to talk about more how we actually implemented that as far as letting dApps use the latest Teleporter version without needing any extra authentication or admin capabilities.
One quick interruption. I think that idea was actually Aaron's with using the off-chain upgrade mechanism. I think I was quick to support it, but I think it was Aaron's original idea. The other quick interruption is someone asked in the chat, which I think is a good question just to tie up here before we move into it, is how does the relayer work? And so maybe you guys could talk specifically real quick just about it, how the relayer actually work and like what security, assumptions there are there in this model.
Yeah, absolutely. So the warp relayer, or the AWM relayer as it's called, is a necessary component of the whole warp flow. And its high level responsibility is when there is a message sent on one chain. In order for it to be delivered to the destination, someone needs to aggregate the BLS signatures of a sufficient amount of the validators of the source chain, put that aggregate signature and the message into a transaction, and send that transaction on the destination. So how you do that is totally up to you. It could be done from a wallet interface for all we care, as long as you have some mechanism to actually query validators for those BLS signatures and construct the aggregate signature, and you have some wallet on the destination to be able to send a transaction. That's all you need. We implemented the AWM relayer as a service to be able to automatically relay any teleporter messages, and then can be easily extended to relay any type of warp message in the future, because we don't want to put that burden necessarily on the user to relay their own transaction. But a key point of the whole design is that anyone can be a relayer. There's no level of, or no additional permissions that a relayer needs other than what everyone already has, as far as just being able to query the source chain validators for those signatures and then broadcast it on a transaction on the destination. There's no permissions given to a relayer in Warp by any means. It's not trusted. And while you do need to construct that aggregate signature, it can only be constructed by the validators, or by querying the validators for their signatures originally. So I think that answers the question. Hopefully also shows how the AWM relayer is one possible implementation, and one that we think will be very, very useful right off the bat, but it is by no means the only implementation. The relayer at a theoretic level is just querying for the signatures, putting them in a transaction, broadcasting it.
Yeah, to summarize there, it's something happens on chain or off chain, but we'll keep it on chain for now. Like, I don't know, export funds. All the validators, when they see that message get accepted in the block, they just sign it with their BLS key. That BLS key that then gets aggregated. And that trick is who actually does the aggregation, right? They don't take on any security property of, like, they're not trusted in any way, but the destination chain, so like the C chain or something like that, only understands this like multi-signature version of the key of the signature. And so someone just has to collect those individual signatures from the validators, turn those into a single multi-signature, and then submit it on the destination. So you can have some hosted service run it, because you don't want to like have to maintain a balance on the destination to basically import that message. But if you do have a balance on the destination, you as a wallet can just query some API, collect the signatures, and then just submit it yourself. So when we talk about like anyone can be a relayer, I think the ultimate vision here is that you as a wallet, if you're commonly interacting between two chains, can just bring your messages yourself, which is a really nice property, just to make sure there's like no censorship concerns or anything like that. But yeah, let's continue with the upgrade strategy.
Cool. Before going to the registry, I guess there's some high-level design principles that we started off with before deciding on this registry implementation. So the first point would probably be security. Trying to make sure that we don't introduce any new bugs, or just make it as easy for dApps to integrate with the teleport as possible. So that's probably the biggest reason in terms of why we went with the registry, and why we wanted to make sure that the teleporter contract logic itself was non-upgradable. So each version of teleporter, V1, V2, the state would be completely separate. and the logic would be completely separate between each version. Another big design principle would be flexibility for dApps to integrate. We wanted to make sure that different dApps built on top of Teleporter would be able to select each version of Teleporter that they'd like to interact with, and not have changes that we push to new versions automatically push onto them. For example, if there's a long-standing version that tends to be the most popular version and has all the features that a certain dApp needs, then they can simply pick one of the older versions and don't have to upgrade. And then another design principle was just ease of integration. So just making sure we can make it as easy as possible for developers to build on top of Teleporter with the registry, whether it's through documentation or just extra calls or extra utility contracts that we support in the Teleporter repo now. And the last point is just minimizing changes to the Teleporter contract, the Teleporter messenger contract itself. So the Teleporter contract, we've gone through quite a few audits to make sure that there's no new bugs or just unexpected use cases from the contract. And at that point, the registry, we wanted to make sure that we didn't have to change the Teleport contract itself too much. And that is supported through the registry contract, where we had to make minimal changes to Teleporter at that point. Yeah. And then now we can just dive into our actual implementation of it, called the Teleporter registry, which basically on a high level is just keeping track of different versions of Teleporter contracts and the addresses that are that the Teleporter versions are deployed to. Like Michael said, we wanted to make sure that the Teleporter registry could be interacted with through a permissionless way of upgrading for subnets. And our approach of that was through warp off-chain messages. So another context for warp message is that when you submit a warp message on chain, you will have the field of the origin chain ID as well as the origin sender address. So normally if someone sends a warp message on chain, it will include their EOA or contract address in terms of the origin sender address. One feature for the warp off-chain message that we leverage is that you can specify any origin sender address in that custom warp off-chain message. So the way we verify that in the Teleporter registry is that we make sure that the warp message that is performing the upgrade was submitted off-chain, and it can only be submitted off-chain if the origin sender address, or it can only have an origin sender address that is the 0 address if it is submitted as a warp off-chain message. So that's the main distinction of how we check that the Teleporter registry was upgraded with a warp off-chain message. Yeah. And then
just to pause for a second there, a lot of people have asked us like, hey, like didn't warp come out like December 22nd, like 2022? Like, why is it taking so long to get it usable? I think these sort of nuanced conversations should be a good indication of why. Not only was there a need to introduce a precompile into the EVM to be able to efficiently verify these BLS multi-signatures, which is something that other ecosystems are considering doing as well, because they're typically used in ZK stuff. But in this case, we not only have the verification of individual BLS signatures, but also they look up state on the P chain in terms of like the current validator set to determine the stake weight of any BLS multi-signature. So adding that support into the EVM was one big step, but then the other big step is obviously what is the developer experience on chain, right? If it's this like crazy non-common thing or like just basically just the precompile expose, it's pretty difficult to actually build cool applications. And so a lot of work has gone into, if we had the ideal wrapper around like this sort of precompile, what would it look like? And the idea was for this is Teleporter, and that like it adds all these useful primitives of being able to update handling of different messages, the relayer to be able to like sponsor transactions across different networks if you want to, things like that, which is as we talked to a bunch of developers, very much a required property here. So, but yeah, on the upgrade side, bugs happen usually is the way I describe that. Obviously, we never want them to, but people may want different things, or we may even add additional functionality as well. And so having some ability to upgrade stuff without having like some single control key or even like a multi-sig is a really nice property for like a network to really own the teleporter interface rather than like some individual or small set of individuals.
And just to kind of highlight how far that's come as far as the developer experience, if you scroll down a bit there in that example app contract, Patrick, you can see it's just inheriting teleporter upgradable, and that's it. Out of the box, when your cross-chain application inherits teleporter upgradable, then you can just call send cross-chain message, and when the network collectively decides that it wants to switch to a new teleporter version, your app will automatically use that new version. But the only way for it to be upgraded is if the network validators are willing to sign off on the new teleporter version. But as far as like application developer interaction, it's really kind of set and forget, just inherit it. And you will automatically send messages using the latest version when those versions are deployed and then added to this registry by the network.
Yep, exactly. We wanted to make it as easy as possible for dApps to integrate with the registry. And what we came up with was Teleport Upgradable, which is basically just a utility contract that lets you integrate with the registry. Yeah, like Michael said, once you inherit it, you have all the properties in terms of once a new version gets added to the registry, then you'll automatically use the newest version for sending. And we also provide some utility functions in terms of making sure you can still receive messages on different versions. And for dApps that have different access controls, we wanted to make sure to provide some kind of safeguards that you'll have to implement in order to protect some of these properties, which is called check teleport upgrade access. And any dApp that has different access controls, for example, whether it's ownable, whether it's a multi-sig, and so forth, or governance, can all implement their own upgrade access for all of that. One of the examples that we implemented was just the ownable version, which is just called Teleporter Owner Upgradable. Yep, and you can see it's pretty simple. You just need to implement your own upgrade access control, and then that's pretty much it. And then the dApp itself can just inherit from that contract. Yeah, and at that point, anytime a new version gets added to the registry, your app will automatically send messages with a new version. And then we also provide some features in order to make sure that you can still receive messages on different versions that you specify to make sure you don't drop any old version messages of Teleporter. One new key feature I guess I want to point out was that because the registry is submitted through off-chain message or upgraded through an off-chain message, we wanted to make sure to provide a utility for dApps to easily decide which teleporter versions they want to accept or deny. So a new thing we're adding, we're adding into the teleport upgradable contract is for the ability to pause interaction with certain teleport addresses. So the dApp can just decide, I don't want to interact with this address of teleporter, and just decide to pause interaction with it, meaning it won't receive or send teleporter versions with this address. Yeah, and that should pretty much cover most of a teleporter and the upgrade strategy. Yeah.
This UML diagram is pretty sick. Is this automatically generated from the code now?
Yep, I was looking at different auto generation tools, and this is definitely auto generated. But we probably want some kind of more standardized way of approaching it throughout the repo, I think.
I
When I
love how
first-
good tooling's getting, dude. It's awesome. Yeah.
When I first saw this, I thought that it was like a mermaid diagram in the README, and I was like, someone put their heart and soul into this flow. Anyways.
Yeah, that's pretty cool. So yeah, I mean, so this is the gist with Teleporter. The idea, just to take it one step further, is to say, all right, well, you know, I'm some Solidity developer. How do I use this thing? Right? I'm like launching a subnet. How do I use it? Our hope is to provide 2 to 3 audited production level contracts that you can deploy to use Teleporter in your world of subnets, but then really focus more on the tooling and support of that rather than adding like, you know, a huge library of audited contracts at this time. So some of the initial contracts, I think, as Michael briefly alluded to, was what we call native token bridge. And so let me pull up that PR. I think I tweeted it out before, but just so I know where it is. So the idea here, and I had no contributions to this whatsoever, to be clear. So I'm explaining it just because I'm excited about it. Most people want to use this to take tokens like an ERC20 from the C chain to their subnet and either use that as the native token or use that just as a token on their subnet. We expect this to be the most popular interaction early on with Teleporter. And so we had a lot of questions, which were like, hey, I want to do exactly this, but like how? Like, I want to write the contract, you know, I'm working on it, but I need to get it audited, you know. And basically every person we talked to had the exact same request. And so we figured, you know, if we're going to have any like really powerful demonstrations, examples that are really audited and production grade, this seemed like the most obvious example. So, you know, by the end of the year, we hope to have, we plan to have an example of using this contract with Teleporter on a local network that you can spin up and just see how it feels. So you'll be able to create an ERC20 on a local version of the C chain, send that ERC20 to your subnet, and then on that subnet, use that native token or this ERC20 as the native token, whether that be an ERC20 or Avalanche, the token, and then be able to bring that back to the C chain. So that's what's going to come to Fuji and mainnet if the ACP, I think 30, is it 30 or 31? 30 is adopted. But in the meantime, you know, we can definitely support creating a local network that does this. Yeah. Not sure if there's anything else you want to add on that point.
Just a few interesting technical details on the native token bridge that we worked through. One is the bootstrapping problem of it. So you first need to create your subnet to be able to bridge tokens into it. And in order to send any transactions on that subnet, you need to have some of the native token, if it's an EVM, which requires creating some of those native tokens first before any of the tokens are actually locked to be moved into the subnet. And that creates a really odd state where your native token is supposed to be backed by collateral, but you just created a few native tokens initially that aren't backed by anything and are really just fake money. And the way that we work around this is the amount of tokens that you allocate in the Genesis that are created in the subnet and aren't initially backed by anything is specified in this contracts constructor. So say you create 10 tokens to be able to send a few transactions. Those transactions would be deploying the teleporter contract, deploying the native token bridge contract, and relaying a first message into it. You specify the amount of tokens that are allocated in the Genesis in this contracts constructor, and then the initial amount matching that pre-allocated balance isn't minted. So say you allocate 10 tokens in the Genesis, the contract knows immediately it's under collateralized, if you will, by 10 tokens. And when it receives the first messages saying this many tokens should be minted, it ignores them essentially. It accounts for them, decrementing the under collateralization until it knows it's fully backed on the native chain. And at that point, then it becomes fully functional in terms of allowing tokens to move in and out. The second interesting feature that we put into it is the ability to report back how many tokens have been burned as transaction fees, because the native token of the subnet is then used in transaction fees on that subnet, and those tokens that are burned as part of transaction fees should never be redeemable on the origin chain. So say you have some massively popular gaming subnet that uses AvaX or USDC as its native token. A lot of those tokens have been moved into that subnet. A lot of those tokens have been burned as transaction fees. The collateral for the burnt transaction fees is still locked in that address on the C chain. And 10 years down the line, say that game is no longer popular, we've moved to a different subnet in a different game. You can move all the active tokens out, but the tokens that were burned as transaction fees would still be locked in collateral on the C chain, and be really a target for attackers to try to corrupt by corrupting the validator set of that old or deprecated subnet. So the way we work around this is just reporting back how many tokens have been burned as transaction fees, and actually burning the collateral on the native chain, so that you don't have that ever-growing amount of collateral held on the origin chain that should never be redeemable by anybody.
Does that?
So this is how you burn USDC, or is there's
So does that include the like EIP 1559 burning? Because like the validator rewards are the funds sent to that address are just like the priority fee, right? It's not the base fee, or am I off?
Because neither in the original implementation actually went to the producer of the block, the default is that both are actually sent to the burn address, that it represented something that was actually useful to be the full amount that was burnt, as opposed to just a portion based off of that function that didn't really apply to us, right? Because if we only send the tips to this address as the reward, it's not really meaningful because it's getting burnt, so it's not meaningful to the person receiving it. And it's also not actually representative of the total amount getting burnt. So in the original implementation, what we did was we sent both the tip and the base fee to that address, so it actually represents real value.
Sick.
Yeah,
I noticed there's a certain UML diagram missing as well on this README. So maybe you can talk to Matthew about generating one of those.
Well, we should have Jeff on the next time to talk about the details of this implementation. He was the person who worked on this for the most part. So
Patrick, how many UML diagrams are in the HyperSDK repo, would you say? Is it more?
None that you could see, I guess, but I think there's a lot. Yeah.
Cool. All right, cool. Those will be sick.
Is there like a Golang tool for that people use? Because I'd love to just stuff it full of UML diagrams. I'm trying to get Copilot to like write documentation for me as well, but I think combining that with the UML diagrams could be effective, especially because it's multimodal now. So, yeah. All right. The last thing, second to last thing, but I want to make sure we had time for this one, was something that Steven whipped up yesterday. So I'll turn it over to Steven to talk about this one.
Yeah, so I think a common or critique or feedback from the ACP process right now is that it's kind of hard to actually signal whether or not validators support or object an ACP, at least without kind of doxing themselves. And so what this does is this allows the actual AvalancheGo node to be configured to specify a validator's opinions of an ACP during the network handshake. So as nodes upgrade to support this, what that'll mean is that people can query their info.acps method on the info API and actually see kind of who prefers ACPs, who objects against ACPs, and the total kind of stake breakdown of who is voting for, against, or not participating in the vote of the ACP. So this provides a nice way of kind of providing validators to use software that they're already running and integrate in and kind of signal to the whole network what their opinions are. So this doesn't do any kind of like automated enabling or anything like that. This is purely to just kind of signal people's opinions on the matter. But I really hope that as time goes by, that this will kind of get adopted as the primary way to signal opinions for ACPs, because I think that this is a pretty clean and straightforward way.
Yeah, so this is not a replacement for the straw poll thing. The foundation is the one that manages that process and like sets the rules or recommendations for the ACP engine. We, just based on feedback from the community, felt that there was an opportunity to modify AvalancheGo in a way to make this a lot easier. But if this becomes widely adopted, which everyone we've talked to is like, this is 1,000 times easier than like signing some message and like posting it to a GitHub. So if it is widely adopted, we we'll share it with the foundation, and they may choose to just swap the process to something like this. But yeah, I think the cool thing will be getting some dashboards out there of like, if you can picture like the pie chart, right, of like the abstain, yes, or like abstain, support, object. It's going to be so cool to list it by ACP. So
what might be a cool follow-up as well is if we added metrics for that.
Yeah, more the merrier, right? Like, I think this is a super important mechanism for like validators to be able to participate in, where things are going. And the important thing here, as Steven mentioned, it doesn't like, if you reach a certain threshold, it doesn't like activate anything on the network, but the community should just know the risk of, hey, if 40% of people or 40% of stake weight object to like some change, maybe don't try to run that on the network because people may not update their nodes in protest, which would cause network instability. So if, just to recall again, like the voting mechanism here is whether or not a sufficient stake weight runs the changes. But, I think the community should attempt to consider like running more unanimously supported proposals rather than, extremely controversial ones, but we will see.
Seems like the perfect thing to use Prometheus metrics with labels, which is my favorite thing. So nice.
Yeah, we'll probably do a massive rehaul of AvalancheGo metrics at some point, but yeah, I'm not sure when. If anyone in the audience wants to take this on, I will review any PRs. For sure.
For anyone that can't tell, Steven is really excited and wants to do this himself. He's been wanting to for a really long time. It was a joke. Just ignore him. He's super excited.
Yeah.
All right. So the last topic that we had on the list for today was actually talking about some of the HyperSDK authentication mechanisms. So this is a total change in gears from everything we've talked about so far. So like just to put a capstone on what we talked about before, totally different topic. So in the HyperSDK, transactions are composed of a few things, but primarily action and auth. Now, when I originally came up with that interface, I wasn't thinking deep enough about auth. So, and this was also before we had like a standardized address schema. So the way to like interact with who was actually signing or participating in the transaction required actually like parsing the authentication object, which like I was so naive back then. But like, yeah, so now there's a standard address format. So you don't actually need to parse the authentication to like understand who is interacting. But another thing that came up was that HyperSDK, it's very important that there's support for transaction relaying. So like a sponsor can pay for the transaction of some sort of actor. And in the mechanism, the way it's currently designed, the authentication object actually is responsible for specifying both the actor and the sponsor, which the astute reader will notice doesn't make any sense, because at that point, like the owner of that auth could just name any sponsor or any actor. And so it assumes that the VM basically provides its own authentication mechanisms that are like, clearly safe and clearly not doing that. But as soon as you open up the door to deploying programs that are auth objects, so let's say like someone's like, hey, I want to, my auth, I want to be some sort of ZK verification. Like clearly the HyperSDK can't support the N+1 all authentication scheme. So there needs to be some generic way to provide support. But if you do that, then you open up the door to this massive issue where like whoever deploys a contract can claim whatever they want as the sponsor. So like you could just like have someone else pay for your fees or something. So as we thought more about this, the decision was made, or basically which is I think a really good step forward, is actually separating that. So there will be, instead of one auth now, 2 auths, one of which is optional, which is to have an actor authentication and then what we call a sponsor authentication. So the actor authentication is the actual like person interacting with the transaction on chain. And then the sponsor authentication is the one that actually pays the fees. Now, the actor and sponsor can be the same, but this native support for like transaction relaying means that you don't actually need to have like all this complex logic on chain to figure out who the actor is in a transaction and who the sponsor is and like everything like that. It's just natively provided to the actual execution. So the benefit for this is like, so I think last week or 2 weeks ago, there was a bug when combining meta transactions with some of this multi-call support on on one of these meta transaction handling contracts, and all of the complexity and everything there around EIP like 2771, I think it is because the EVM doesn't support native meta transactions, and so contracts need to add some extra functionality or like introduce routing transactions to be able to add this functionality. And in some ways, I think of like the HyperSDK as, if we're coming after all these other virtual machines, like we should certainly look at the common patterns that we think will be around for a long period of time and find a way, if we can, to natively bundle them into the engine. One of the big ones we've seen, at least from like AvaCloud deployments and everyone interacting with subnets, is this sort of gas forwarding functionality or gas relaying functionality is a huge part of adoption on many of these new subnets. And so adding support for this to make it easier for developers to interact was something that was clearly part of the design early on, but this should make it much, much more powerful because you can now deploy safely custom authentication modules using WASM.
This is really nice. Yeah, this is super cool, especially with all the complexity that comes out of EIP 2771, 712, and all of the different account abstraction that goes into. I mean, there's so many different proposals that there's even more complexity just in the number of different proposals for how to do account abstraction, the EVM, to just separate it cleanly like this, that the actor and sponsor is 2 totally separate things natively is super, super nice.
Yeah, and then people might say, like, is there like a huge overhead to doing that? And the way that it works is basically the sponsor has like a bit or a byte to indicate like if it's populated or not. So at most, it's just like a 1 byte overhead to the transaction. But I think like we'll probably add flags to the transaction with like bits, so it should eventually just be like a bit overhead.
So would that mean that if that flag is not populated, then there's no sponsor signature? Or sorry, if the flag is not populated, then it uses the actor signature for both the actor and sponsor? Yeah,
Exactly.
Cool.
Yeah.
Nice.
Yeah, I mean, if you're using SecP256 recoverable signatures, which I know you're not, you're using ED25501. But if you were, you got a whole 7 bits of V value to play with already. You could, anyway.
So it does support R1 non-recoverable signatures. And so you could add, now that like I've totally ripped apart everything, SecP-K1 with recoverable if you wanted to. So up to you,
I know it supports it, but I also know that
one of the tricky things there is that malleability and the HyperSDK do not mix oil and water. So like you got to find a way to make the signature non-malleable. Otherwise, you can create multiple TXIDs that are valid. So something to keep in mind for the astute reader. All right, I think I see a bunch of comments. First off, I think people were asking a little bit about more Firewood related updates. Firewood is, as you can look, it's all being developed in the open, making progress. I think Firewood folks had a really big milestone last week where they connected Firewood to the MerkleDB tester, which we're using for like benchmarking and larger integration tests. So it's been a long time coming to get to that point, and so now the team is working out bugs and optimizing it based on that. So I expect some updates there, public updates on Firewood's progress, maybe sometime in the next month or so, with production readiness, maybe hopefully by the end of like Q1 or Q2. I think it really depends on how things are going there. Someone made a note about R1 being backdoored. Same could be said about K1 being backdoored. No one knows. That's why HyperSDK gives you options. If you want to use K1, R1, or whatever curve you wrote yourself, go ahead.
My favorite conspiracy theory is that Satoshi Nakamoto is just the CIA, and they just backdoored all the crypto.
This feed's gonna get cut if you're not careful.
Controversial statement, dude. Controversial. But yeah, you can use whatever backdoor you want on the HyperSDK. That's one of my favorite parts about it.
It's generic.
Yeah. But on a serious note, don't implement your own curve. It's probably going to be broken. But I think we're running up on time now, so we'll wrap it up here. Thanks everybody for stopping by, and talk to you later. Thanks everybody.
Thanks everyone. See you.